So the first exercise we did in chapter 7 was the poker chips, okay? And the whole idea behind that exercise was to get you to be convinced that with repeated sampling, if we calculate, everyone calculates their own p-hat values, their own percentages, if we put them all together on a graph, that we could look at the mean of all those percentages and come up with a good estimate for a population, okay? So right here is how good is p-hat as an estimate for the parameter p. To answer this, we will look at an approximate sampling distribution of a particular p-hat. To create the distribution, we are going to use a simulation from this app. All right. According to Wikipedia, which I find a very trustworthy source, even though they say you're not supposed to use it, the proportion of colors in Reese's Pieces is 50% orange, 25% brown, and 25% yellow. Okay, we are going to consider just the proportion of orange, which, by the way, this would be a binomial setting, because if you've got a bag of Reese's Pieces, either the candy you pick is orange or it's not orange, okay? And they're saying that 50% are orange, so 50% are not. And every time I pick a new candy, it's independent of another. We're in a binomial setting, okay? So launch the Reese's Pieces app, set the population proportion to 50%, it is. And click on proportion of orange instead of number of orange. Got it. Proportion. All right. Click on the draw samples button. Okay. Okay, so it just spit out 25 candies, one sample worth, and they got 44% orange. What percent are we, quote, supposed to get? 50. Okay, sampling variability. Same thing with the poker chips. There were 50% red in that bag. Did you get 50% red when you took your sample? Maybe, maybe not. Okay. All right. So that's the first blank right there. Number 2. Okay. What is the proportion of orange? 44%. Is it close? It's close. All right. Now I'm going to turn off the animation. And I'm going to turn off the animation because we're going to be doing a whole bunch of samples now. Change the number of samples to 500. Okay. Keyboard. I have a keyboard here. I can do this. There we go. All right. So delete, and I want 500. Did that work? Nailed it. All right. So we're going to start over. Okay. We're going to start over. Okay, so we'll reset everything. All right, we're starting over. All right, we're good. All right, leave the number of candies at n equals 25. All right, again, this is another time to emphasize n equals 25. That's how many candies they're drawing, but they're going to do it 500 times. So this is going to be your approximate sampling distribution. Okay, so draw the samples. Okay, so there are 500 dots now on this graph. Okay, there's 500 of them. And this is the most recent, was 36%. So that one came in like over here. But overall, is it centered around the 50% like we would expect it to be? It's somewhat normal. And it's centered, it looks like it's centered around 48 to 50. Okay, so in this case, I look at this, that seems to work. All right, so let's fill in our table here. Proportion of orange Reese's Pieces is supposed to be 50%. We did n equals 25. We have a mu of, my summary statistics. The mean was 0.495. The sigma was 0.1. And shape, I would call that approximately normal, wouldn't you? Of course you would, because you're not going to contradict me. I wouldn't lie to you. All right, so now we're going to reset. You guys wrote those down on your table. You got the 0.495 and the 0.1. approximately normal? Okay, I'm gonna reset. So that's all gone now. I'm gonna leave 500, but this time I'm gonna draw 50 candies at a time. So I'm gonna change the 25 this time. Change the 25. Get rid of the 25, put in the 50. Got it. All right, here we go. Here we go. Ready? Boom. All right, now the mean is 0.503. The sigma is 0.071. And the shape, you with me? Still approximately symmetric? All right, reset. Now we're gonna draw 100. I'm gonna get rid of that 50. We're gonna put in 100. Draw. All right. Mean, 0.502. Standard deviation, 0.051. Shape, still approximately normal. This literally is exactly what you did with the poker chips. It's literally the exact same sort of sampling exercise, just the repeated sampling. We're just dealing with bigger numbers here. You guys had an n size of 20, and there were what, only like 13 of you. Okay, now we're dealing with n sizes of 100, and they're doing it 500 times. Okay, so we're just dealing, it's the same sort of exercise, but bigger numbers. All right, so now I'm gonna kind of switch it up a little bit because this is a binomial setting. But, and I don't know if you remember when we did the binomial distribution, I talked about that if you have a binomial setting that's a 50-50 split, I said you generally will have an approximately normal distribution. Do you remember me telling you that if you don't have an approximately 50-50 split, it's going to end up being a skewed distribution? Okay, so if you had a 15% success and an 85% over here, okay, then all of a sudden you're going to end up with a skewed distribution. So what I'm going to do is, even though this is the Reese's Pieces app, I'm going to do M&Ms, because plain red M&Ms, according to M&M Mars, they do only 13% red. So I'm going to put us into an off-balance binomial setting, a 1387, okay? And let's see what happens. So I'm going to reset this. So it says probability of orange. Well, in your head, make it say red. Does it say red in your head? Good. So I'm going to get rid of the 50%. I'm going to put in 13%. And I'm going to go back to only 25. And I'll stick with the 500. Okay. Cool. All right. So now in the table under number 6, the mean is now 0.13. Okay, well, we're back. The very first question on the paper, how good is p hat at estimating p? Pretty good. Okay, these p hats came in as low as 0, as high as 32%, but they still had an average of 13%. So to answer the very first question on the paper, how good is p hat at estimating p? It's pretty good. Okay, now, what would you say about the shape of this distribution? Is it still approximately normal? It kind of is, but if you look at it closely, can you see a little bit of the skew over here? Can you see a little bit of that tail? Okay, that's the 1387. Okay, that's the 1387 because it puts you off balance a little bit. Okay, so you're going to get a little bit of a skew going here. All right, so let's switch the 25, reset, and we'll switch the 25 to a 50. and draw. Mean, 0.129. Standard deviation, 0.045. And can you still kind of see a little bit of a skew on that one? Again, at a glance, is it kind of approximately normal? Yeah, it kind of is, but you can still, I actually think I can see the skew a little bit better on this one. Okay, just that little bit over there, just a little bit. Okay, nothing too severe, but let's reset it and let's go with 100. Let's go with 100. Right? So then after this, I think I'm done with our little app for the day. Come on, draw. All right, mean is 0.131. Standard deviation is 0.034. And the shape, all right, it's approximately normal. I mean, really all of them, I'd say they're approximately normal. But this one may be a little bit of a tail, but it doesn't look very strong over here. I mean, there's just a couple of little droplets over there, okay? The bottom line is, as your end size gets bigger, you start losing more of the skew, okay? As the end size gets bigger, you tend to start losing more of the skew, okay? And we're going to talk more about that. So you guys wrote all these numbers down. I didn't. But I have numbers from last year that I kind of referred to, and they might be similar. Who knows? Maybe they're the same. Maybe these apps are like your calculators that it defaults to the same numbers each time. I don't know. Where is my stuff from last year? Right here. All right, actually, just help me out. What do you guys have for, help me fill out the table. What do we have? All right, let's stop right there. All right. What do we have from last year? Okay, they came in different, so it really is random every time. They came in different. What I want you to notice on these is, again, back to the very beginning, how good is p-hat at estimating? I think it's pretty good. Okay, they came in at about 50%, whether I only selected 25 candies at a time or whether I took 100 candies at a time. But what I want you to look at is the standard deviation. And I'm going to put a couple of decimals on here just to make it easier to compare. So we went from 0.100 to 0.71 to 0.51. Do you see that as your n size gets larger, your standard deviation is getting smaller? Okay, there's an inverse relationship there. All right, so that is in a binomial, call it a binomial 50-50 setting. This is a binomial 1387 setting, okay? So in this case, these were all approximately normal, very clearly. Now these down here, now ours came in, it wasn't as severe as I've seen other years, again, because it really is random, but these, they start approaching approximate normality, okay? So the larger your n size, the more likely it is that even if you start off balance with a skew, if you get a large enough n size, you can actually approach approximate normality, okay? Help me fill in these values. Bless you. All right, so same idea. Even though a 1387 binomial setting, it gives us a little bit of off-balance skew, we still have really good estimates for the proportion of 13%. And once again, as your n sizes are getting larger, do Do you see that your standard deviations are getting smaller? Okay, there's an inverse relationship here. I also put a comment here, said from this point forward, if I just refer to sampling distribution, assume I'm talking about an approximate sampling distribution, that we're talking about the sampling distribution that came out of our example, as opposed to the large, authentic sampling distribution, okay? All right, so summaries on this. The summaries are this. The shape. Sampling distributions are approximately normal. But it will depend on N and P. Because it depends on if your P is 50-50, you are going to have approximately normal. If your P is 13 versus 1 minus P being 87, you might see some slight skew unless your N size gets large enough. N and P work in conjunction with each other, okay? If you have a P and a 1 minus P of 50-50, you're probably going to be in decent shape. You're probably going to have an approximately normal distribution. But if your P and 1 minus P start getting off balance, 1387, or reverse it, 8713, you might have a slight skew unless your N size is large enough to compensate for that, okay? Center. The mean of your sampling distribution, which I will call in this case mu sub p hat. I think yesterday I might have called it x bar sub p hat, whatever. The bottom line is we're looking at the mean of all of the p hats on the same graph. The mean really is an unbiased estimator of P, the true population proportion. It is, in fact, very trustworthy, okay? The spread. Sigma sub P hat. So your standard deviation of all your P hats on your sampling distribution gets smaller with larger N sizes. And I'm going to say again, it depends on N and P. N and P work in conjunction with each other. The standard deviation decreases with larger N sizes. But how would we know exactly how much? Okay, when we look at those numbers on the other page, you can see the standard deviations got smaller as the N sizes get bigger. But do we just leave it at that, or can we actually quantify it and say how much? And the answer is we can quantify it. And we're going to go through an algebraic proof to develop a couple of new formulas. You ready? I know you guys love algebra. I do. I like algebra. Oh, we have room right here. That's why I saved the white space here. Okay, right here. So we are going to start with let x equal a random variable. All right, and just so you kind of, just to have a visual of what I mean, x is a random variable, I'll just say over here, like for example, x could stand for the number of orange Reese's Pieces. And I already kind of walked you through. It's like, you know, you're in a binomial setting because it's orange or not, 50-50. Everyone is independent of another. And we're picking exactly 25, or we're picking exactly 100 or 50. Okay, so we satisfy our bins. Okay, but let's just say x is any random variable. Since it is a binomial random variable, we have some formulas that came from our formula page. Okay, formulas for binomial random variables. Those formulas were mu sub x equals n times p, and sigma sub x was n times p times 1 minus p, all under a square root. And I'm going to remind you again, those formulas, they're on your formula page. Okay, I gave you that packet at the beginning of the year, and I give it to you at every test. Those formulas are there. Hey, we're just on your exam. Do you remember, did you use them? I hope so. All right. But now what we're going to do is relate it to what we're learning about now. We weren't dealing with counts of orange Reese's Pieces. We were dealing with percentages. So we calculated p hat. Okay, think back to your poker chips. You calculated your p hat by saying, how many red did I get out of my 20? Well, so if x is how many I got, I would have to divide by how many did I draw. This was the math that you were doing on your poker chip example right here, okay? But if x is a random variable, I should be able to apply these formulas in here. So what I'm going to do is I'm going to break this apart. Do you agree that x over n would be the same as 1 over n times x? Because x times 1 would give me x, and then there's an n on the bottom. All right. By writing it like that, though, what I've now done is I've set that up as I'm transforming a random variable. I'm taking the random variable x and I'm transforming it through a multiplication procedure. And the rule for transforming a random variable was, I should be able to take the mu for x, okay? I should be able to take the mu for x and multiply by that same number, and it should give me the mu for my p hat. All right, so let's now combine this with this. So I'm going to do a substitution on this. This is going to get substituted with this. So I'm going to turn this into 1 over n times np, but then the n's would cancel, and the answer is just p. What we just mathematically showed, we showed why p hat is an unbiased estimator. Because this says if you take a whole bunch of p hats and you look at the mean of all of them, it will be equal to the p for the population. This literally is just algebraic proof of why p hat can be used to estimate p. Now the sigma one is a little bit more challenging, but the rule for transforming a random variable is I should be able to take the sigma for x and also multiply that by the 1 over n, and that should give me the sigma for p hat. And what I'm going to do now is I'm going to take this and substitute it with this. And I'm using ovals and circles and rectangles to make sure you remember which ones I'm substituting where. So when I substitute this, I'm going to have the 1 over n, but that's going to be multiplied by, all right, I'm going to do a little bit of fancy stuff here. I'm going to separate each one of these, or actually at least I'm going to pull this. I'm going to take the n and give him his own square root, and then I'm going to leave the other guys underneath the square root. So now the n's don't completely cancel. But what does happen is I can cancel the square root with this, but it's going to leave a square root now on the bottom. Okay. Either you follow that or you don't, but it might help some of you. Do you remember how a square root is the same as a 1/2 power? So if you think of that numerator as n to the 1/2 power, and you think of that denominator as n to the 1st power, remember that rule about how you can subtract exponents? Okay, so 1 minus 1/2 would give me a 1/2 powers left over, but it's left over on the bottom. That's why the square root's left on the bottom. But now that they're all under square roots, I'm going to put them back all under the same square root, except now the n is on the bottom. Star, star. Those are important formulas. The good news is they are so important. Can I flip the page? Are we good? Are we caught up? They are so important that when you flip the page, you'll see I have a note. They are on your formula page. Okay, they're there. It comes back to, again, you have to know when to use them. Okay, they're going to be there, but you have to know when to apply them. Okay, and that's going to come with practice. So here's your formula for the mean of a sampling distribution, the standard deviation of a sampling distribution. All right. And I think it was in chapter 6 that we first looked at these, what I call conditions. We talked about our 10% rule, and then we did your n times p and n times 1 minus p have to be greater than 10. Some people say greater than 5. Okay, I use 10. But these are going to be important. And at some point, I'm going to show you, I'm going to pull up an AP free response scoring guideline and show you that even in their scoring guidelines, those are there. Okay, this is not Mrs. Fry making something up. Okay, I don't usually make stuff. I don't usually lie to you guys. Sometimes, not usually though. All right. About 75% of young adult internet users ages 8 to 29 watch online videos. Okay, I think that's low. But all right, who knows when this problem was written? This would be an example of a population parameter. That would be P is equal to 0.75. Now you might say to yourself, well, if we already know what the population parameter is, why do we do anything with this? Why are we going to do any sampling? Well, through the process of statistical sampling, you could confirm whether that was accurate even at this time, okay? So suppose a sample survey contacts a simple random sample of 1,000 young adult internet users. That's your n size. N is your sample size. And based on the results, they calculate the proportion p hat who watch online videos. So what would the mean of the sampling distribution be? Well, you know what? This is not meant to be a trick question, but it's an easy one. There's a formula that says, if you know the population parameter, that should be the mean of your sampling distribution. So if I know that P is 0.75, and I know that mu sub P hat is equal to P, then if P is 0.75, then mu sub P hat probably comes in at about 75%. just like what we saw with the Reese's Pieces. They said 50% orange. Every time we looked at a graph, it came in centered at 50% orange, okay? So now, you are required to check the 10% condition. The 10% condition simply says that you got a picture in the whole population of adult internet users, okay? That's your capital N size. You understand every time you select one person from that group, you now have one less in your capital N. So technically it changes the probability of the next person getting chosen. Do you remember the example I did with the NASCAR, the cereal boxes? And every time you bought a box of cereal, it technically changed the calculation, but it changed it so minimally that we said, don't care, right? That's what this condition is saying. We have to make sure that we have sampled less than 10% of the population. So what you want to do is confirm, is your 10 times your N, is that less than or equal to capital N? Now our lowercase n, our sample size was 1,000. Do we know what capital N is? I don't. But you know what? Can I assume that there are more than 10,000 young adult internet users out there? Can safely assume more than 10,000 young adult internet users. I'm going to tell you guys right now, on your test for me, on your AP exam in May, you show the math and you write a statement explaining what the math tells you. You explain why you did that math. Okay, you don't just do the math and call it done. Okay, my analogy in that is that's like, you know what? I think just right now, I think I'll write on my paper that 2 plus 2 equals 4. Yup. Is it relevant right now? No. It's the same thing here. Don't just show somebody some math that you did. Explain why it's relevant. Okay, so you do the math and you write a statement that explains why that's important. Okay, so now I said find the standard deviation of the sampling distribution. All right, so the standard deviation for p hat is, again, you're going to have the formula page, but you use it enough times, you'll know it. You take your p-value, which was 0.75, your proportion. You multiply by 1 minus p. So that's when I'm always talking about a binomial setting. I'm like, okay, it's a 75-25. You divide by how big was your n size of your sample. In this case, it was 1,000. And you take the square root of the whole thing. And you should be able to type that in a calculator just all in one step. You can just pull up a square root and you can just go straight through and go 0.75 times 0.25 divided by 1,000. You don't need extra parentheses. Order of operation should all be fabulous. So I'll call it 0.014. So this is how you can actually quantify how much does the standard deviation decrease, okay? So we saw it happening here. We saw these standard deviations going down, but mathematically, why was it going down? Well, because as your n size got bigger, you kept dividing by a larger number. And so it makes the whole answer get smaller and smaller. This next question, I have literally seen these on AP exams, so be ready for this. They're going to give you a specific new n size and say, okay, how would the standard deviation change? What if our sample size were 9,000? Now you might look at that and say, well, that's not hard. I'll just redo the formula and I'll put a 9,000 in. That'll work. So I'm going to take that same formula. Instead of 1,000, I'm going to put a 9,000. And I'm going to square root it. So I'm going to redo the math. Oh, what I have here. I need a square root button. I need 0.75 times 0.25, and I divide by 9,000. 0.005 approximately. And you're like, that's cool, I'm done. But what they'll do to you on the AP exam is they'll say, by how much did it change? Did it grow by a factor of 3? Did it decrease by a factor of 1/3? Did it double? Did it cut in half? Now, you could figure this out, even estimating. If I take that first answer, 0.014, and I divide by 0.005, 2.8. In other words, this one is almost 3 times as large as this one. That's what happened. It was a factor of 3. Now, mathematically, why? It's this right here. What I'm going to do is I'm going to rewrite this problem. But what I'm going to do is I'm not going to just write 9,000. I'm going to write 9 times 1,000 so that you can actually see both problems kind of in the same one. Okay, if that 9 wasn't there, that's the first answer, right? But now the 9 is there, that's the second answer. But what if I pulled that away? If I pulled that away, I would have a square root with a 9 on the bottom, and then the rest of that's going to be back underneath its own square root. And put a 1 there. So now do you see that was the first problem? But now this is mathematically what we did to the second problem. But what is the square root of 1/9? 1/3. So you can very quickly see that by increasing my n size by a factor of 9, I decreased my standard deviation by a factor of 3. I reduced it. I multiplied it by 1/3. Okay, and you'll know when that type of problem comes up. I'm telling you, they'll do it. You'll recognize. Like, notice they didn't ask you about 5,000. They gave you 9,000 because they knew you'd be able to take the square root of 9. They might do a 4,000 or a 16,000. They'll give you perfect squares, knowing that it'll make the math come out really nice. Okay. Using the original n size of 1,000, so going back to the real problem, check conditions to confirm that we have approximate normality. The issue is, on this thing, we're at what I call a 75-25 split. That would make a slightly skewed binomial distribution. Okay, well, n and p work in partnerships. So what you're going to do is you're going to multiply n times p, which in our case, n was 1,000, p was 75%, and then n times 1 minus p will be 1,000 times 25%. So what do we have? 750 versus 250, right? Are those both greater than or equal to 10? Yes. We can assume the sampling distribution is approximately normal. And I'm going to give you the same reminder that I gave you on the standard deviation and the 10% condition. I will be looking for this calculation and this calculation and a statement why we care about that calculation. Don't just put the math. Every year I have people do this. They write it down and they literally put like a check mark saying, yup, and then they go on. And again, I'm back to my analogy. Don't just plop some math on your paper without an explanation of why you put that math on your paper. guideline from an actual AP 3 response exam. Now, it's old. This is 05. It's old, but look what they have. Now, don't worry about like the subscripts, but they have n times p, 13 is greater than 10. N times 1 minus p is 65, and or 65 times 0.8, 52 is greater than 10. It is reasonable to assume that they produce, okay, so they have these explanations that go with it, okay? This one they don't so much here. They did on a different one that I closed. But the observations are independent. It is reasonable to assume that 65 boxes are a random sample. It is reasonable to assume that they produce more than 650 boxes of the cereal. They don't just do 65 times 10 and end it there. They provide an explanation that goes with it, okay? So when you do those, I want explanations to go with them, please. Now, why do we care about normality at all? Well, we care about normality because it allows us to use we can use z-scores. So now it says, what is the probability that we get a result of 78% or more? What is the probability that our p hat comes in at 78% or more? Now, we know that p is 75%, or at least that's what they told us. Do you think it's reasonable that someone might get 78%? Sampling variability, right? Okay, so let's find out. What's the probability that z would be greater than or equal to? All right, now we calculate our z. We are trying to convert 0.78 minus. We need a mu. We need a mu sub p hat. What is mu sub p hat? 75. Divided by, we need a sigma sub p hat. Oh, look, we did that right here, 0.014. And I have that comes out to be a z-score of 2.19. You'd whip out your calculators. You would do a normal CDF, and you would get an answer, hopefully, of 0.0143. What you need to understand is how to interpret that. And I will stop here because I know we're out of time and we'll come back to that. But you definitely have enough information. You should be able to do this homework. Anytime they ask you about this 4-step process, they're just reminding you to go through all the steps.